Everyone, today we talk about the topic 3, the phase lock loop, and we are trying to monitor or say estimate grid or tested signal frequency and angle so that we are able to synchronize whatever voltage we generated to those grid voltage. So first of all, let's go through the single phase PLL block diagram and Simulink model. At the beginning, what we know is a tested signal in sinusoidal waveform. We're assuming we only have fundamental component here with angular frequency of omega here. So we can tell at different time moment t, we can have different position of this test signal omega t. So we are trying to estimate or say track the position and angular frequency omega here. So what we need to do is introducing first of all a orthogonal signal of this tested signal. Orthogonal signal of a sine is cosine. Therefore we have Vm same magnitude times cosine omega t, same angular frequency here. So with these two signals, we put them through a algorithm introduced in the lecture, and out of this algorithm we are having two new signals, V1 and V2. They're in terms of a Vm, cosine or sine, parenthesis theta minus theta hat. Here the theta is the real position angle of the tested signal, and the theta hat is the estimated value. So obviously we want the theta equals to theta hat, so that we are saying we are successfully tracking the position angle of the tested signal. So how to make that happen? Alright, so by carefully observing V2 here, we can tell if V2 is equal to 0, then the sine theta minus theta hat is equals to 0. Then we basically can say theta is equal to theta hat, or say they're very, very close. So this is successfully tracking the tested signal position angle. So what we really need to do is, in real time, keep regulating V2 to be 0, so that we can keep tracking the theta by estimating the theta hat. Therefore, this is the resulted control block diagram in where we are regulating V2 to be reference value, which is 0. And 0 is compared to the estimated or say calculated V2 to have an error going through a PI controller to estimate the theta hat, actually as well as the angular frequency omega hat. So the subsystem down here is nothing but the implementation of the algorithm up here. Which has 3 inputs. The first one is the tested signal here. Second input, cosine, is the orthogonal signal of the tested signal. And the third input is the feedback estimated theta, used to estimate the V2 as well as V1. However, V1 we don't do anything about, so we only output V2 here. So this is the algorithm block diagram for the single phase PLL. Okay, so based on the developed diagram, we can go ahead to do the modeling in MATLAB Simulink. So here's the developed modeling in Simulink. And inside of this box here, obviously we are seeing the single phase PLL, and which is a typical very basic closed loop control system we learned from ECE 360. We are trying to regulate the V2 to be 0 as the reference here, and we are applying a PI controller to regulate that, and estimated position angle theta hat is feedback to help find the V2 hat and to be compared with the reference 0. And in here we are not only be able to estimate the position theta hat, we also can estimate the angular frequency omega hat here. We will see the result. So both angular frequency and position. Out of this box, we're seeing this part. This is trying to make the output position angle to become periodic, bouncing between 0 and 2 pi, or say 360 degree. And what we are doing is, instead of showing the theta hat here, which is a straight ramp line from 0 to infinity, we are trying to find the remainder after division with 2 pi. So we are going to be able to see a sawtooth-alike waveform, periodic between 0 and 2 pi. Okay, let's talk about the input section. This is the input part of the system. So we are seeing clearly two inputs. One is the tested signal, Vm sine theta, whose position angle and angular frequency gonna be estimated by here and here, and the orthogonal signal of this tested signal, and therefore we have Vm cosine theta. So these are the two inputs. By using a switch in front of it, I'm trying to introduce a dynamics, in the sense that when the time clock is greater than 0.2 second, I gonna pass through these two inputs. Otherwise, or say before that 0.2 seconds, between 0 and 0.2 second, I gonna pass through these two inputs. So here we can see the frequency is actually 30 Hertz. And after 0.2 seconds, the signal becomes 60 Hertz. So actually this part is input part are actually having a dynamics happens at exactly 0.2 seconds. Before that moment and after that moment, we have two different frequency, two different positions. We will see that from the output. And this portion is trying to observe the estimation of the angular frequency, omega. So these are the actual angular frequency to be compared with the estimated one here. So we will see how they work. So we run the simulation for 0.5 seconds. Obviously, we need to be greater than 0.2 seconds to involve that dynamics. So let's first of all observe the input signals. Yellow one is our tested signal. Blue one is the orthogonal signal of it. Obviously, you can see from 0.2 the frequency changed. Before that, we have smaller frequency, 30 Hertz. After that, we have double frequency, 60 Hertz. So we will see how the estimation of the position angle is. Here is the position angle. Obviously, we can see it can track the dynamics. So before 0.2 seconds, it can show exactly 30 Hertz. Okay. Position angle start from 0 degree to 2 pi here, which is exactly consistent with the tested signal cycle. After 0.2 seconds, since the input signal changed to be 60 Hertz, our angle position is following that as well. So still beginning from here, 0 degree to this 2 pi, exactly follow the tested signal frequency. Here, this yellow line, we might need some zoom in to see clearly. So yellow line is the actual angular frequency, And the blue line is the estimated value, so they fit each other very well after some dynamics, of course, because of the control system nature. So this is the Simulink model and how we interpret the result. So this is a second example for three-phase PLL, a steel block diagram and Simulink model. So at the beginning we need three-phase tested signals, or say three-phase voltage. From here we can see they are balanced, meaning same magnitude, same angular frequency, and 120-degree phase shift. And also we can see either positive sequence or negative sequence, it doesn't matter. So we can still apply the same algorithm to estimate the three-phase voltage position angle and the angular frequency. So the algorithm is like this. We first of all put these three signals through Clark transform followed by Park transform to come up with so-called VD and VQ. So by Clark transform, we are transforming original three-phase AC here to two-phase AC, okay, which is transformed to two constant DCs through Park transformation, which apply actually the position angle theta here. So the idea to track or say estimate the position angle theta is, instead of regulating V2 in single phase, we are regulating VQ in three phase here to be 0. So here we are applying a similar closed loop control mechanism as we did in single phase PLL. First of all, 0 reference value for VQ, compare with the calculated VQ value out of Park transformation, and error goes through the PI controller to estimate both angle frequency and position angle here. And angle position is feedback to the Park to assist the Park transformation. Three inputs here for the Parks are the three original balanced three-phase voltages. So this is the block diagram and Simulink model for the three-phase PLL. Alright, so based on that developed diagram, we also do a modeling in MATLAB Simulink, and here we go. As in the single-phase PLL, we are having this closed-loop control mechanism contained inside of this box, and so we are trying to regulate the VQ to be 0 by this closed loop feedback the estimated theta hat to help to come up with the estimated VQ, and then compare with the reference value 0 to be regulated by PI controller. So not only the position angle theta hat, but also the angular frequency omega hat could be estimated here. We will observe the result for both. Still applying this mod to observe the sawtooth alike waveform periodic. So input side, three phase, of course, and by using the switch, I'm introducing again the dynamics at a certain moment, which is 0.15 second here. Before that moment, we have this set of three-phase voltage in where we can see 25 Hz frequency and positive sequence. After 0.15 seconds, we are having another set different three-phase voltage with 50 Hz frequency and negative sequence. So we will be able to observe the frequency, position angle, as well as the sequence from the result. So after running the simulation, we are able to first of all observe the tested signals. From here, we are able to see obviously two different sets of three-phase voltages. Before 0.15 seconds, we have three-phase voltage with actually 25 Hz. And after that moment, we have 50 Hz three-phase balanced voltage. They also have different magnitude, which doesn't affect the estimation of the position angle and angular frequency. So let's take a look at the result. First of all, the estimated position angle. Yep, the boundary of dynamics happens at the point 15 seconds exactly, and before that we have 25 Hz three-phase voltage. Position angle is ramping up, indicating the positive sequence from 0 to 2 pi, which is approximately equal to 6.28. After the moment, we have a higher frequency, actually double, 50 Hz, and the ramping is going down, which indicates the negative sequence, as well as the angular frequency here, positive angular frequency and negative angular frequency. Also, if you stay in the V alpha, V beta, and VDVQ, we can also observe them according to the concept we learned from the lecture. After going through the Clark transformation, the three-phase AC becomes two-phase AC with 90-degree phase shift. There are exactly 90-degree phase shift between V alpha and V beta. We can tell that. And also, after the Park transformation from there, we are able to obtain actually two constant DC, VD and VQ. Since we are regulating VQ to V0, we should be able to observe a zero constant VQ down here. Okay. Going through dynamics as well at t equals to 0.15 seconds. And VD is step up. So these are the results for the three-phase PLL and the simulation, trying to help you understand the concepts better.